In the world of machine learning, data isn't just a collection of numbers, it's a story waiting to be told. Often, this story is about how different variables interact, how they dance together. Understanding these relationships is fundamental for building effective models, from predicting outcomes to identifying key features. Today, we'll unravel two critical concepts for measuring these relationships: covariance and correlation. Before diving into formulas, let's visualize. The simplest way to see how two variables relate is through a scatter plot. If the points generally go up from left to right, we have a positive relationship, meaning as one variable increases, the other tends to increase too. If they go down, it's a negative relationship. One increases, the other decreases. And if the points are scattered randomly, there's no clear linear relationship. Now, how do we quantify this? Enter covariance. At its core, covariance tells us the direction of the linear relationship between two variables. It helps us understand if they tend to move in the same direction, both increasing or both decreasing, or in opposite directions. Think of it as summarizing how much two variables vary together relative to their individual means. The formula for covariance involves summing the products of the deviations of each point from its respective mean, then dividing by n1. If both x and y are above or below their means, the product is positive, contributing to positive covariance. If one is above and the other below, the product is negative. A positive covariance indicates a positive relationship, a negative value indicates a negative relationship, and a covariance near zero suggests no linear relationship. The larger the absolute value, the stronger the linear relationship in that direction. While covariance tells us the direction, its magnitude is tricky. The actual number you get depends entirely on the units of your variables. For example, if we measure height in centimeters, the covariance will be a much larger number than if we measure it in meters, even if the underlying relationship between height and weight is exactly the same. This makes it impossible to compare covariance values across different datasets or variables with different scales, limiting its practical interpretability. This unit dependency is a significant drawback for covariance. We need a way to measure the strength and direction of a linear relationship that isn't affected by the scale of our variables. We need a standardized measure. This is where correlation comes in. Correlation essentially takes covariance and normalizes it, dividing out the influence of the individual variable scales. The most common type is the Pearson correlation coefficient, often denoted as R's. Its formula is simple. It's the covariance of x and y divided by the product of their individual standard deviations. This standardization ensures that R always falls between -1 and 1, regardless of the variable's units. A value of 1 means a perfect positive linear relationship, -1 means a perfect negative linear relationship, and 0 means no linear relationship. Values closer to 1 or -1 indicate a stronger relationship, making R universally interpretable. Let's look at some real-world examples. Consider the relationship between the number of hours a student studies and their exam grade. It's intuitive that more study time generally leads to higher grades. This relationship would show a strong positive correlation. As one variable increases, the other tends to increase in a predictable way, giving us a positive R value, perhaps around 0.85, indicating a strong positive link. Now, for a negative correlation, think about the relationship between average daily temperature and the sales of winter coats. As temperatures rise, fewer winter coats are sold, and vice versa. This inverse relationship would result in a negative correlation coefficient, perhaps around 0.7. This means as one variable increases, the other tends to decrease, indicating a clear, moderate negative connection. Finally, an example of no correlation. Is there a relationship between a person's shoe size and their IQ score? Intuitively, these two variables are completely unrelated. If we plotted data for many individuals, the points would be scattered randomly, forming no linear pattern. The correlation coefficient would be very close to 0, like 0.5, telling us there's no linear relationship whatsoever. So, To recap, covariance tells us the direction of a linear relationship. A positive value means variables move together, negative means they move inversely, and 0 means no linear relationship. However, its magnitude is scale-dependent, making it hard to compare. Correlation, specifically Pearson's law, resolves this by standardizing covariance. It gives us both direction and strength, ranging from -1 to +1, making it a universal and interpretable measure. In machine learning, correlation is generally preferred for its clarity and comparability, especially when exploring relationships or selecting features.